So we are going to start off with the next topic on the unification scheme, and we're going to talk about the grand unified theory today. This basically comes up to something which we call as gut. Okay, so scientists had this gut feeling that definitely the energies or the forces which we are talking here can be unified. The grand unified theory is basically a theory. Experimental evidences are still not available. So this is basically a story that we are going to listen to. There are a lot of theories, a lot of new theories which are being developed, and some of them are well accepted till date. And this is basically formed on the basis of right from when the Maxwell's equations started, when his theory, his field theory was given. Based on that, these ideas are developed, and slowly with time, scientists believe that these actually can be something which are more real. You must have also heard about something which we call as theory of everything, where there is also the idea that all the four forces or the interactions will basically be combined. So this is a very interesting image that I actually have got from this particular website. Okay, and here there are two images, so this is more interesting. So you have the forces, and basically this is something which is there. Okay, and then we know that electromagnetic force is because coming from the electricity and magnetism, for which Maxwell forms the basis. And then definitely we have got the weak forces which actually acts at a distance of, let's say, 10 to the power minus 15, 16, 17, in that range. Okay, as a strong force obviously is within the nucleus. And then when this electroweak and the strong force usually combines, we get something which is called the grand unified theory. Okay, there must be some kind of super force, because what happens is these combination will only act when the energy is very high. Okay, which was actually there when the universe actually began. Okay, but then the doubt is, since this is all theory, is this even possible? Okay, do the three forces really merge out? Okay, so this is something which we are going to look into it from a theoretical point of view, and let's just read these important points here. Okay, so what happens is an attempt to describe all the fundamental forces and the relationship between the elementary particle in terms of a single theoretical framework. So what the term that we should remember is something which we call as the theoretical framework. So everything is theoretical right now. Okay, experimental evidences, probably the nearest experimental setup which can provide is nothing but the CERN setup. Okay, so what happens is, in physics, forces can be described by fields. Okay, so that meditates interactions between separate objects. So when we consider an electric field or a magnetic field, the forces that acts between them can be actually described by that particular field, and they are of course between two different objects. So what happened is, in the mid 19th century, okay, in the late 1800s, James Clerk Maxwell actually gave his four equation, if you remember, and that actually led to the formulation of the first field theory, and what we came to know as a new branch of physics, which is nothing but electromagnetism. Then in the early part of the 20th century, Einstein came in, okay, in the 1910 1920s, and he developed the general theory of relativity, a field theory of gravitation. So we know that when we combine quantum and general theory of relativity, even special theory of relativity and so on, we basically get something which is called the quantum field theory. And then we have the contribution of Einstein's in there. Okay, but then later Einstein and also some other scientists tried to construct a unified field theory, not this grand unified theory. It was a different unified field theory, where they actually tried to talk about electromagnetism and gravity together. Okay, as a part of a single fundamental field, but they failed at that point of time. Okay, and then to this day people are still trying to combine gravity, but it remains it away from this unified field theory. It becomes a very difficult task to achieve. Okay, so if we consider something like subatomic particles, so we know that something which we can look into from a macroscopic point of view, we usually apply the Newtonian mechanics or classical mechanics. But when we look into and go deep into the system, we basically look into the subatomic system, and then we describe everything in terms of the quantum field theory. So in the 1940s, the quantum electrodynamics started taking shape. Okay, and the quantum field theory of electromagnetism became fully developed. So when Maxwell said about this, the picture was more or less classical, but later on in 1940s it became quantum, and then we have the quantum electrodynamics, a part of which we have also studied in this syllabus. So when we talk about the quantum electrodynamics, the charged particle usually interact as they emit and absorb photon. So photon was more or less detected, okay. People knew about photon, the detection was there, okay, and we know that these are nothing but minute packets of electromagnetic interaction. So we basically have two charged particles. The interaction that happened was because of the photon, okay, and then we call this as nothing but the game of subatomic catch. So two particles which are charged in nature caught the photons within each other, and that is the exchange of particle which led to their interaction. Now this theory was so well known at that time that it became a prototype of the theories of other forces. So it was believed by the scientists that this theory was good, and if people started working on this theory, they can develop more and more and ultimately reach the final goal of theory of everything, or even before that, the grand unified theory. So then in the 1970s and 1960s and 70s, subatomic particles started becoming important because some particles were already being started to be detected, okay, and they basically form the two bases of building block for the materials, and these are nothing but quarks and leptons. So whenever we talk about quarks, we know that they exist within the neutrons or the protons, or more specifically within the nucleus. So quarks usually takes part in strong interaction, okay, so they are always bound, okay, and of course they are bound by this short range force which overwhelms the electromagnetism at subnuclear distances. So they overpower the electromagnetic force at the subatomic distances or subnuclear distances within the nucleus, and more or less responsible for a very strong force, okay. So the leptons, which basically includes the electron, do not feel the strong force, and the leptons are more or less responsible for the weak interaction as such. But then quarks and lepton both experience a second nuclear force, the weak force. Of course the nuclear force is far stronger, okay, but then they do experience that weak force as well, okay, but in general if we talk about leptons, they experience more of the weak forces. So we need to know that what are the particles that are responsible for weak force and strong force, or which particles are taking part in weak force and strong force. So in the year 1970s, when quantum field theory for the strong force developed, it was basically called as the quantum chromodynamics. So basically we are talking more or less about the quarks here, and we also talked about something which we call as the colored quantum number and so on, because chromo comes basically from the word color. So in quantum chromodynamics, quarks interact through the exchange of particles called gluons. Now these quarks are responsible for a strong nuclear force. So if we consider two charged particles and there are photons which are getting exchanged between these two charged particles. So similarly, if we consider two quarks, there should be some kind of particles which should get exchanged, and these exchanged particles are basically nothing but called as gluons. So these gluons are responsible for the strong nuclear force. So the aim of the researcher is basically now to discover whether the strong force can be unified with the electroweak force. So we already had the electroweak force, which is a combination of the electromagnetic and the weak force, and now we want to combine it with the strong force, and this aim actually led to the development of a new theory which is called the grand unified theory, which was built on the basis of the same logic as electromagnetic and weak force. So this evidence that the strength of the forces vary with energy is such that they converge at a very high energy. Now here I'd like to show you a very simple graph. So what happens is, if you basically plot a graph between energy and forces, so this side maybe we can consider this as energy, okay, and as we go from left to right, the energy keeps on increasing, and this side we have the forces. So initially what happened, at some energy the electroweak and the grand unified forces combined. So at this particular energy we had the electroweak and the weak forces, sorry, the electromagnetic and the weak forces combined at this particular energy. So we have this. But then if we go further, and we have, let's say this is our strong nuclear force, this is the strong nuclear force, and then this will actually again get further and he will combine with this. So at this particular range, that means at even a further higher energy, we are actually having a combination of electromagnetic, weak and the strong force. Now this energy is in the range of giga electron volts. Okay, so this is something which is said here, that the strength of the different forces vary with energy in such a way that they converge at a very high energy. So if you want to combine electromagnetic and weak force with the strong force, we have to go even to further higher energies. So the energies involved are extremely high, and as I mentioned, it's in the range of giga electron volt, more than obviously million times as great as the energy scale of electroweak unification. Now this electroweak unification has been verified by experiments. Okay, so we do have experimental evidences for this, but its combination with a strong nuclear force, the experimental evidences, well, we are still searching for that. So the grand unified theory describes the interaction of quarks and the leptons. So leptons are basically responsible for the weak forces, and quarks are responsible for the strong forces. And if we consider the grand unified theory, it talks about the interaction between these two. Okay, but then with the same theoretical structure. So we have to bring the same theory and combine these two, write down an equation basically which can actually talk about these two together. So this basically gives rise to the possibility that quarks can decay to leptons, and specifically that protons can decay. So what happens if you apply a very high amount of energy? The chances are that proton will decay and get into constituent quarks. So that means proton must have some kind of lifetime. So the early attempts of grand unified theory actually predicted that the proton's lifetime must be in the somewhere in the range of 132 years. But then this prediction, which was actually tested in experiments by applying a very large amount of energy, it was found that proton did not decay. So it obviously pointed towards the fact that it is possible that the lifetime might be even greater. This was predicted by the simplest of the grand unified theory, and hence we can say that at this juncture this really did not work, and it could not give a correct explanation of the lifetime of proton. But then this is also an evidence to suggest that the strength of the forces do not converge exactly unless new effects comes into play at higher energies. So that means if proton had that much of lifetime of 1032 years, and let's say it has been proved, then at higher energies they can converge, okay, keeping the same theoretical framework. But since this did not happen, another new effect was actually studied, which basically is called as the new symmetry, or called the supersymmetry. So if there is symmetry, there should be something which is called asymmetry. So if you look into it from a theoretical point of view, we can say that at the beginning of the universe, all the forces, weak, strong, electromagnetic and gravitation, was together, and as time went on, and there was the Big Bang explosion, or whatever you may call it, these energies started to deviate and they were no more together. So that means that actually resulted in a kind of asymmetry. So at the beginning it was symmetrical because all four of them unified, but as time went on, all of them separated out, and then it was actually resulting in something which we call as asymmetry. So a successful grand unified theory, this is just a theory as we all know, will still not include gravity. So even if you consider something like supersymmetry, the still inclusion of gravity becomes a big problem here. Here actually the theorists do not yet know how to formulate a workable quantum field theory of gravity. So a workable quantum field theory of gravity, something which is needed to explain it theoretically, but then the physicists or the theorists were not yet sure about it, okay, based on the exchange of hypothesized graviton. So graviton evidences was not there, so that also became a problem. Now since actually we talked about supersymmetry, let's just give a brief about supersymmetry, although it's a very huge topic, a lot of ideas are there. But supersymmetry usually predicts that there is a partner particle for each particle of the standard model to explain why particles have mass. So supersymmetry is not a replacement of the standard model, it is definitely a extension of standard model, and Higgs boson also comes into the picture. So standard model actually has shown a lot of facts, okay. We have actually amalgamated all the particles and the exchange forces within one basic basic theory, and this basically forms the building block of matter. But then physicists recognize that this is incomplete. Now initially we actually have seen some drawbacks of standard model, so definitely it's incomplete. So new theory needs to be incorporated, but we are not replacing it. Supersymmetry is basically nothing but an extension of the standard model that basically aims to remove those drawbacks of the standard model. Okay, so it predicts that a partner particle for each particle in the standard model. So each of the particle will actually have a partner particle in the standard model, and this new particle will actually solve the problem which is called the fixing the Higgs boson's mass. So as per prediction, the mass of Higgs boson should be different, but theoretically it's something, or experimental observation might show something different, and so on. So this kind of fixation needs to be done, and this is actually done by the supersymmetry theory. Okay, so if the theory is basically correct, if it is believed, then supersymmetric particles should appear in collision at Large Hadron Collider. So if this theory of supersymmetry is to be believed, and whenever the Large Hadron Collider experiments are conducted where high energy protons are actually allowed to collide to mimic the Big Bang, there should be some supersymmetric particle which should also come into the picture. And as I said, the supersymmetric particles are nothing but the partner particles of the particles which already exist in the standard model. So the standard model usually predicts all the particles should be massless. Now theorist basically has come up with a mechanism to give particle masses that requires the existence of a new particle, the Higgs boson. I would just like to tell you something which is not believed totally, but if you consider the forces, we know it's electromagnetic, gravitational, weak and strong, but the result, the mass is because of the Higgs boson. So a part of the scientific community also believes that the involvement of Higgs boson gives rise to this fifth kind of interaction which is actually possible. But then coming back to the topic, it is basically a puzzle why the Higgs boson should be light, as interaction between it and the standard model particle would tend to make it very heavy. Okay, so Higgs boson is basically light, okay, should be light, but the interaction between the standard particles will make it very heavy. So what happens is the extra particles which is actually predicted by supersymmetry, that means a particle which exists in combination with the particles in the standard model, will cancel out the contribution to the Higgs mass from the standard model partner, making Higgs boson light as possible. So what happens is, if we consider the combination of let's say the standard particles, okay, and the Higgs boson, it predicts that the mass of Higgs boson should be heavy, but then prediction is the mass should be light. So that means there should be involvement another additional particle, and as per supersymmetry, that additional particle is actually existing in combination with the other particles of the standard model. So there is involvement of another particle. So this new particle that we are talking about would interact with the same forces as standard model particle, but they will definitely have different masses. Now if these supersymmetric particles are included in the standard model, the interaction of the three forces, that is the electromagnetic, the strong and the weak nuclear forces, could have existed at the same strength but at a very high energy as in the early universe. So when the universe began, the energy was very high, and as the energy came down, all these forces started to divert and basically got separated from each other. So if we want to go back to that situation where we want to combine the three forces, that is the weak, the strong and the electromagnetic forces, we again have to recreate a very high energy system which is in giga electron volt, as I told you in the previous slides. So supersymmetry would also link the two different classes of particles known as fermions and bosons. So if we really consider supersymmetry, it will also link fermions and bosons, and as a result we can combine the three forces. Now you know that fermions is basically nothing but half spin particle, and boson is a one spin or the integer spin particles. But then if we consider something as half spin, it basically follows the Pauli exclusion principle that no two fermions can occupy the same quantum state. So they are more or less very standoffish. That means they are more or less standing separate with each other. So fermions, it says that it should be in a different state all the time. But on the other hand, if you consider something like boson, they are very clannish, so they belong to a same clan. So they prefer to be in the same state, okay, even if in the same quantum state.
So these are nothing but referring to the standard model, and supersymmetry basically predicts that this boson and fermion combines. So in general we can say that a single spin particle which is having a full spin, let's say an integer spin, will actually combine with a half spin. Okay, so bosons are accompanied by fermions and vice versa, and this is predicted by the supersymmetry theory. Okay, so this supersymmetry actually talks a lot of surprising things. Okay, so if we just look into the final conclusion, in many theories scientists predict that the lightest supersymmetric particle to be stable and electrically neutral and to interact weakly with the particles of the standard model. They are exactly the characteristics required for dark matter. So in general, if you want to explain dark matter, we again have to take help from supersymmetry. Okay, and then which makes up most of the universe and to hold galaxies together. Basically, the standard model, as we have seen before, one of the drawbacks, it does not provide a proper explanation for dark matter. Supersymmetry that builds up the standard model's strong foundation to create more comprehensive picture of our world. So it gives a better explanation of the standard model. But then we also have some of these questions about the inner working of the universe. We still don't know, and the entire picture can actually be painted by using these theories like supersymmetry and all. Okay, so that's all for today. Thank you.